Hi everyone, welcome to this online talk on physics of language models, part 1, context-free grammar. So this is an expanded version of the talk I have been giving offline, and it contains more materials. To begin with, I will show you a little prelude that coincides with my talk a few days back. That is, I generally work on the theory of language models, but the word theory can really mean a full spectrum of things. On one extreme, there is mathematics or learning theory, in which we prove rigorous theorems. But on the other hand, we have to make assumptions, right? So there are a lot of cons with respect to this type of math approach to study the theory of language models. In particular, the assumptions we make are sometimes very idealistic, and the networks we can analyze are sometimes very shallow, like a two-layer transformer, and so on. So this is like how the math approach roughly looks like. And on the other extreme, there is also something that I would call as a metaphor, ethology. That is animal behavior science, in which you play with, for instance, ChatGPT or Llama 2, and you can design tasks to see if they are capable of doing that, and you can draw conclusions from there, right? In this way, you can study super large language models. You can make also educational conclusions, but at the same time, the conclusions you can draw are usually less rigorous, too subjective, and even highly debatable. And this type of ethology approach may also sometimes lead to false claims. So in my mind, there is another important issue with this type of approach, that is, it tells us really very little about how and why the transformer works, or if it fails, then what's really going wrong behind the scene. So for such reason, I have been really thinking about, if there really anything that's a sweet spot between the two. So this is an area that I would call it also as a metaphor, physics, in which I'm emphasizing on four things. Number one, I wish to do controlled experiments, so I can control the data, pre-train or fine-tune data. And at the same time, I want the experiments to be highly repeatable, so that we can really try a lot of different configurations of the data, of the model, and so on, of the training process, and so on, so that whenever you want to make any conclusion about, for instance, is language model capable or incapable of doing something, you really had better have tried all of the possible configurations before you make such a scientific conclusion, right? But this also necessarily means that we cannot study models that are too big. We probably can only do it within like a billion parameter scale. So in this way, the experiments can be highly repeatable. But don't worry, we don't need to analyze the entire notion of intelligence or AGI using GPT-2, right? We can decompose the notion of intelligence into building blocks, and then maybe study them one by one. Finally, I want to emphasize on this probing aspect, especially for today's talk. That is, with such a smaller scale of the network and with such synthetic and controlled experiments that you can control the data and so on, then it makes it much, much easier to actually probe into the network, into the transformer, to figure out what's happening behind the scene. So this is an area that I would call it physics. As a metaphor, I probably would not call it neuroscience, because to me, like neuroscience, maybe back to 10 years ago, was more like you buy 5 monkeys, you design 20 tasks, and then you try to put maybe 30 electric probes into their brains, and you try to collect data. But here we're talking about really growing monkeys from scratch. You can grow like tens of thousands of monkeys yourself, and you can also design thousands of tasks. And more importantly, you can put like millions of electric probes into the transformer, like everywhere, like at different layers, different heads, and so on. So this is like more like experimental physics in my mind. So as I said, we can decompose the notion of intelligence into building blocks. And a few days back, I was giving a talk on knowledge, storage, extraction, and manipulation. And today I'm talking about a totally different building block inside this notion of intelligence. This is context-free grammar. Okay. So before I even introduce what is context-free grammar, let me ask, I think, a very crucial and fundamental question. That is, what do we previously understand about the inner workings of transformers? I want to particularly highlight two results that I really like, and I think a lot of people have read them. The first one is this induction head notion that has been popularized by Anthropic. That is, they observed in a pre-trained transformer, there are certain attention heads that are in charge of doing the following logic. That is, whenever it sees, like on the input sequence, there is something like A, B, then blah, 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 A, then actually it knows to generate the next token to be B. So this is like a mathematical induction. And they observed that in transformer, actually, there are certain attention heads in charge of doing this. So using this finding, you can interpret the transformer on fulfilling the following tasks, such as sequence copying, translation, and pattern matching. But then how about like more complex tasks? And how about more complex induction heads? So in that same paper by Anthropic, they also emphasize that fully reverse engineering, like large language models, may really be intractable, and they don't have a strong framework for mechanically understanding that. And they even hypothesized that matching and copying more abstract and sophisticated linguistic features, rather than the precise tokens on the input, may actually happen at deeper layers of a transformer. But they did not give experimental evidence for this. So that is the induction head notion. And another paper I really like is this interpretability in the wild paper from Jacob Steinhardt's group. So they actually managed to reverse engineer transformers on a very interesting task. That is, if you keep saying like English sentences, like for instance, when Mary and John went to the store, then John gave a drink to who is the next, what is the next word, right? And as human beings, we know it's Mary. But if you switch this from John to Mary, then the next thing should be John, right? So you see that there is a little bit logic happening behind the scene, and this is not something that can be easily explained by induction head. So they reverse engineered the transformer and noted that the transformer will also learn something like inhibition head, so that he learns that whenever the previous name is John, then the next name had better not to be John, and so on. And there's also some name mover head that's in charge of like moving a name to later of a sentence. And there's even a backup name mover head that says like, if the name mover head fails, then there's a backup one that tries to fill in. So that's a very interesting paper to read. That is, they really reverse engineered transformers like to a very interesting extent. But they also mentioned that to the best of their knowledge, at least when they wrote the paper, that was the most detailed attempt at reverse engineering a natural end-to-end behavior in a transformer-based language model. So you see that our understanding to the inner workings of transformers are still quite limited, especially like what if we have a very recursively defined language or logic? Then can we like probe into the transformer to understand like much deeper in the network what is happening, instead of like looking at something that's maybe only on the input token level. So this is why we want to introduce this notion of context-free grammar. To begin with, what is context-free grammar? So it's a language defined by a set of rules. For instance, from the root, you can apply the first rule to go to ABC, or you can apply the second rule, and suppose you apply the first one. Then from there, you can keep applying, you can select a rule from A to generate, for instance, to BE, or you can select B and pick one of the rules to generate DD, and so on, and you can let this process continue. And in the end, if all of the symbols can no longer expand, then you stop, and this is one sentence that satisfies this the above defined context-free grammar, okay, or CFG for short. So we call those symbols that showed up on the left-hand side non-terminal symbols. So those are the symbols that have specific rules that you can apply to further expand it. And we call the remaining set of symbols terminal symbols. For instance, the capitalized or uppercase symbols are terminal symbols in this example. Okay, so context-free grammar is, can be formally defined like this, and I'm pretty sure that most of you have seen at least some examples of context-free grammars. For instance, the coding grammar or the programming language grammar can be described in this way, and the English grammar can also be defined in this way. Okay, so there are a few properties I want to, two properties I want to especially highlight about context-free grammars. That is, number one, CFGs or context-free grammars can capture very long-range planning. So if you think about it, suppose we have this parenthesis matching kind of grammar. Then what is this next token X? Is it like curly bracket or like square bracket or and so on? And is it opening or closing? This actually highly depends on something that could happen really, say, hundreds of tokens before it, right? So locally speaking, if you only look at, for instance, here, then you may not be able to determine what is X. You have to really do some long-range planning to look at things that were, hundreds of tokens before, and you may need to do some counting and so on. So this is certainly not captured, for instance, by induction hack, right? So that's one property about the CFGs. And another property I want to emphasize is that it can be locally ambiguous and highly locally ambiguous. For instance, we have in this CFG example here, we have C that can be expanded to G, right? But if you see GG, like in a sentence, their parent may not necessarily be C. It could be that BD also generates to DGGF, so therefore the GG may actually come from there, or maybe like BCD also generate to like 4 G's in a row, so that the GG can be like any pair sitting here. So therefore, like just by looking at consecutive terminal symbols, you may not be able to uniquely determine what are their parents. So this is what I would call it like locally ambiguity of CFGs. And keep in mind that not all the CFGs are locally ambiguous. For instance, the bracket matching example is not really locally ambiguous, because locally, if you look at some consecutive symbols like left, left, right, right, then you know that they must be combined together. You know what their parent is. But at the same time, English grammar is also not so locally ambiguous. So without going to the definitions here, but you can imagine that if there are certain terminal words that have certain special properties, what they call like RBJJ or maybe JJPP, then their parent can be uniquely determined. That is the ADJP. So therefore, like English grammar, sometimes, at least locally speaking, can actually be parsed using greedy. So that's not very locally ambiguous. And for such reason, in order to test language models' ability to really learn like very complex CFGs and very locally ambiguous CFGs, we actually introduce our own set of synthetically defined CFGs. Here is one example. So this is the CFG that we call CFG3F. It's one of the dozens of CFGs that we synthetically constructed in the paper. And let's highlight on this one first. So to begin with, notice that this is a layered CFG. So on layer 1, there's only the root node. On layer 2, there are 3 symbols, 3 non-terminal symbols like 19, 20, and 21. And on layer 3, there are also 3 symbols, 16, 17, and 18, and so on. So on the level 7, or also known as the terminal level, we only have 3 symbols that are 1, 2, and 3s. So that is a layered CFG. And we make it layered because it will make our probing easier, so that we can more easily talk about, for instance, non-terminal symbols at a certain layer, and we can correspond that to some transformer layers, and so on. And also the expansion rules that we consider here are of length either 2 or 3. So we don't want to consider a fixed length CFG, because otherwise then you will have like a fixed length of the output that will make the CFG too easy. So we consider like the lengths of being either 2 or 3. And also, in principle, for a CFG, then you can also define some probability for each rule to be applied. For instance, given like an NT symbol of 19, you can define 3 probabilities, each corresponding to like what's the probability you apply the first rule, the second one, and the third one, and so on. But in our paper, for simplicity, we just assume the probabilities to be uniform. So if you think about it, if the probabilities for certain rules to be applied are much lower, for instance, like 10 to the negative 8, then such a rule will be very hardly to be sampled, and therefore like it will make the CFG much harder to learn, right? But I claim that having like non-uniform probability is really an orthogonal dimension comparing to the difficulty of learning a structured, layered, tree-like CFG. And therefore, like we wish to actually disentangle this difficulty from the difficulty of the CFG alone, which comes from the tree side of the CFG. So therefore, like we just do not assume the probabilities to be very skewed, and for simplicity, we just assume the probabilities to be uniform. Okay, so that's another property. And very importantly, the CFG, for instance, this one, CFG3F that we constructed, it's very long and locally ambiguous. That is, if you generate a sentence from the grammar, then here is a typical sentence. So it's long, it has series of tokens, and in particular, like locally, if you look at it, you see like things like, I don't know, 1, 3, 2, 3, 1, 2, 3, then it's very hard for you to determine what is their parent and so on. So it's very locally ambiguous. At the same time, as I mentioned, that the number of terminal and non-terminal symbols per layer is 1, 3, 3, 3, 3, 3, 3, 3, 3. And in fact, we made the number of T/non-terminal symbols as few as possible, because this makes the CFG much harder to learn, and it makes it more locally ambiguous. Think about it. If I have like 10 terminal symbols, then it's much easier to infer what are their parent, right? So I intentionally made the number of terminal symbols as few as possible, like having only 3 terminal symbols. This way can make the language more ambiguous, and I, at the same time, also made the intermediate non-terminal symbols to be of only 3 possibilities for each layer for similar reasons. So that's another property about the CFG3F data that we generated. Yet, I claim that our CFG is defined in such a way that the global parsing tree is mostly unique. That is, if you look at the entire input sequence X, then, for instance, you can do dynamic programming to do the parsing, then you're going to get a unique global solution in most cases with high probability. So this is another property of this synthetically constructed CFG. And as I said, the standard way to parse a sentence, even when the CFGs are given, then to parse a sentence into the tree, actually that requires dynamic programming, right? But here we are talking about even a harder task. That is, we're asking a transformer to learn such CFGs without the CFGs being given. So in principle, if you think about it, that's a task that is even harder than the most naive version of dynamic programming. And finally, I want to mention that this is a very hard CFG because there are about 10 to the 80 number of strings satisfying this CFG. Among, for instance, 10 to the 140 number of possible strings of length 300 or more. Okay, so the sentence from the CFG could be of length like more than 300 tokens. And I'm just saying here, for instance, if you randomly generate a string, there's no chance that you will satisfy the CFG. Or if I give you, for instance, a prefix of 50 tokens and ask you to complete to satisfy a CFG, then you may not be able to do that by just randomly saying something. So therefore, like this is a synthetic defined CFG, that is actually pretty hard. At least like you cannot randomly say something to satisfy it. So this is a list of several properties I want to mention about the CFG. So in the paper, we actually describe more explicitly like how we generate a CFG like this one and so on. So in fact, in the paper, we prepared at least five kinds of CFGs that are of this kind of format with increasing level of difficulties. Okay, so we call them like CFG 3B, 3I, and so on. So those are some code names. And if you compare that to, for instance, the English CFG, then, as I said, the English CFG are typically much shorter, of an average length of only 28. But our sentences from the CFG are highly ambiguous and also like very long, of like hundreds of tokens. So finally, as a kind of comparison, in the paper, we also created the two more data sets, CFG3E1 and CFG3E2. So the purpose of them is not to have exactly 3 non-terminal symbols per layer. So we tried to increase the number of non-terminal and sometimes terminal symbols. And that is for comparison purpose. As I said, if you increase the number of symbols per layer, for instance, then that will make the CFG much easier to learn. So we will see actually concrete numbers to convince you that those are much easier to learn than the ones on the right, and so on. So those are for comparison purpose. Okay, so in this talk, let's mostly focus on just for instance, the 5 CFGs that are sitting here. Here is question number 1. That is, can we use GPT-2, for instance, small, to learn such CFGs? And recall that GPT-2 small is a transformer that has 12 layers, 12 head, and 768 dimensions per layer. And can we use GPT-2 small to learn such CFGs? To be precise, this is what I mean by learning. That is, I want to use GPT-2 small, for instance, to be pre-trained on the CFG3F data directly. By keep generating sentences from this language, for instance, even with infinite amount of data, or also known as online data. So one can, of course, like also maybe define a fixed size, the training set and test set and so on. But for now, let's think about them just being infinite. That's easier to describe. We do not need another parameter to control the training data size. If you do that, then you will get similar results. But for the talk, let's think about them being infinite. And then let's consider, like, suppose we have GPT-2 just pre-trained on such data, like you recall that was like 1 to 3, 3 to 1, and so on. So very locally ambiguous. Then could it learn anything about this language? And our first main finding of the paper is that actually transformer learns such CFGs just by looking at those like very ambiguous like 1 to 3, 3 to 1s, and it can learn the CFG like almost perfectly. So this is what do I mean by that. First of all, we can look at the generation accuracy. That is, we can, after the pre-training, we can let the model generate from like a start token, and then we can check if its generation actually satisfies the CFG, so using temperature 1. Or we can also check the completion accuracy by, for instance, first generating a correct sentence from the CFG, then we take a prefix of length 50 and feed this into the language model, say GPT-2, and let it do a completion from there, just with this correct prefix. And then let's check if the completion generated by the language model under temperature 1, for instance, is in that language of CFG, right? To check if its completion is correct. So we can check, for instance, those two kinds of accuracies, and here's what we found out. Here we are comparing, for instance, the vanilla GPT, which uses absolute position embedding, versus at least 2 more like modern versions of GPT that uses like relative position embedding or maybe rotary position embedding. So those are denoted by GPT-rel or GPT-rot, for instance. And we see that, for instance, on this CFG3F data, the one I have shown you like on the previous slide, then the vanilla GPT actually performs pretty bad on the two tasks. So one is generation accuracy. I denote this by cut 0, and the completion accuracy, I denote this by cut 50 because I use a prefix of length 50. So the accuracies are pretty bad. But if you switch to the two modern versions of GPT, then the accuracies are much, much higher. So this is actually a first minor takeaway message from today's talk, that is the modern variants of GPTs, for instance, using relative or rotary embedding is actually quite crucial. Not to say even to parse the real life like knowledge, the real life language, but even just to parse a grammar tree. This is already pretty important to do relative or rotary embedding. So we should really abandon absolute position embedding. So that's like a first takeaway message. And then at the same time, we also compile to, for reasons that shall become actually clear at the end of the talk, we also compile with like two weaker versions of GPT, in which like the first one we call GPT positional. It means that we use only positional-based attention, so that whenever we have attention like I attend to J, then that attention weight only depends on the positions I and J. We let it to be trainable, right? It does not depend on the input. So that's like what we call the positional-based attention. And we also tried the uniform attention, in which like there are a few attention heads, for instance, 8 attention heads. Then each, say the 8th attention head looks back at exactly 2 to the h minus 1 tokens with a uniform weight. Okay, so we call this uniform attention. So those are definitely much weaker versions of attention, but we notice that they also perform relatively well. Not as good as the state-of-the-art versions of the GPT, but actually much better than the original vanilla GPT. So that's like another finding that we will come back to this actually at the later part of the talk. And the two more observations here is that, as I mentioned, our 5 main data sets are of increasing level of difficulties, and indeed, like the performance of the GPTs are also like degrade if you go from top to bottom. And finally, there were the 2 data sets I put on the site. I said that's for comparison purpose, the CFG like 3E1 and 3E2. So those are the ones that have more terminal/non-terminal symbols, and that indeed made the CFG much, much easier to learn. So the accuracies are close to 100. So this is like our very first result that shows that for the CFGs that we synthetically constructed, especially the modern versions of the GPT are very capable of learning them in terms of generation accuracy and completion accuracy. But if you think about it, those 2 accuracies may not necessarily reflect everything about the learnability. For instance, for the generation accuracy, as a model, if I just successfully memorized one correct sentence from the language and I keep just saying the same sentence, I just keep saying the same thing, then the accuracy will be 100%, right? Okay, of course, for completion, that would be much harder. But for instance, maybe I can, to some extent, memorize a little bit about for each prefix, then what I should say, spell out. So therefore, like just by looking at the accuracy alone, that may not be a complete study about whether or not the transformer learns such CFGs. So for instance, we had better also look at generation diversity. Okay, so how to check generation diversity? There are at least 2 ways to do that. The first, like a more naive way, is to look at entropy. We can estimate the entropy of any distribution by using the sum of the log of the conditional probabilities of the sentences. We can do this estimation. And if you do this estimation, here is what you will find out. So we also compile against the ground truth. We have the ground truth distribution, and we can also compute the entropy over there, right? So I'm using bits in this table, so that whenever you see a number like 268, so that means the entropy, the size of the site, the size of the language is at least like on this magnitude, that is 2 to the 268. Okay, so that's the entropy bits. And we compare that against all of the other transformer models, and we check the entropy of their outputs, and we see that at least they're on the same magnitude for each row, right? But if you think about it, entropy estimation is also maybe pretty weak, because even a model that just keeps generating like random sentences, then it may also have a large entropy, right? So for instance, if you connect this back to the accuracy, then you see bad accuracy here, but you don't see any bad entropy here. And therefore, like just by looking at this entropy alone, it may not necessarily be the best kind of estimation, but it's at least one estimation that we did. Now back to this generation diversity. Is there any better way to look at diversity? So we actually also proposed in the paper to study, instead of just looking at entropy as a single number, right? Can we look at, for instance, how many distinct sentential forms you can generate from any symbol at a level of the CFG to another level of the CFG? So if like L1 equals to 1 and L2 equals to 7, then that just means how many sentential forms you can generate from the root to the leaf. But we can study something like in between. How many sentential forms you can generate from level 2 to level 6 in particular. How to do this estimation? We borrowed the idea from actually this very nice paper by Aurora and Zhang. So I think this idea must date back to much earlier, but it was actually the first time I learned this. That is, you can use birthday paradox to actually lower bound the support size of any distribution. For instance, if you draw m samples from a distribution, and if all of the samples are distinct, then you know that with good probability, the support of that distribution should be at least on the magnitude of m squared. This is birthday paradox, right? Let's use this idea to actually check. For instance, if we generate 20,000 sentences from either the ground truth CFG or from the GPT learned CFG, then we can parse them using dynamic programming and do some counting to check for collisions and so on. So let's see what we find out. So this figure is actually a very complex figure to read. I will read this with you, but it captures everything I said above. So let me explain. The rows here represent the starting symbol. That is, from which symbol I begin this generation. Okay, and the columns here represent where do I stop. That is this L2. Okay, and for instance, the cells here, those like blue or cyan blue area actually represent that. For instance, in the ground truth, that is the correct CFG distribution, then if I start from NT symbols like 16, 17, and 18, then if I go from there, which are on level 3, and I generate to level 5. Okay, this column means level 5. Then I have about like 100 sentential forms, because the color is about here, that I can generate. Okay, so that's like what the colors mean in this table with respect to the ground truth and to the output of other models. And more importantly, as I said, I'm checking for this collision counts. So here the white numbers actually represent the collision counts. For instance, the 3 zeros here represent that if I start from NT symbols like 21, 20, and 19, and I generate from there, which are on the second level of the CFG, until the 6th level of the CFG, then I have no collision, like 0 collisions. So that means by birthday paradox, with good probability, there are at least like 20,000 squared sentential forms from those symbols to NTs on level 6. And not to say that if you look at the upper right corner, that just means you have at least that number of sentential forms from the root to the leaf, and so on. So this is a very hard figure to read, but the most important message from here is that actually, no matter like which model you use, then their diversity pattern, no matter if you do the pure generation or you feed it with a prefix and let it complete, then the diversity pattern of the output, all of them actually match very well to the ground truth, including the collision counts, in which, like, occasionally you have maybe one collision somewhere on the boundary, but they're mostly like 0, right? So this is, I think, a more convincing argument that the output generated by the GPTs, by the language models, are actually very diverse, and they are diverse also in the same way comparing to the ground truth. So that completes the generation diversity part. So I claim that in order to convey the point that a transformer learns such CFGs, not only we have to look at the accuracy diversity, but there's another important aspect, that is the distribution. That is, for each sentence, are we generating it using the correct probability, like comparing to the ground truth? So of course, like, we cannot directly compile the two distributions because the support size is more than like 10 to the 80, right? That's too huge. But at least we can do some maybe like a weaker version of the comparison. For instance, how about just looking at the marginal distribution? We can compute PAI to be the probability of the anti-symbol A sitting at position I. Okay, not only we look at the terminal symbols, but even for non-terminal symbols, what's the probability of that to be on position I after parsing, right? And we can calculate the distributional patterns, and this is the ground truth, and those are the outputs from the distributions from the output of the GPT, and we can subtract them to see the difference. So from here, we see that once again, if you use the vanilla GPT with absolute positional embedding, then the difference is much bigger. But if you use like the relative attention or the rotary embeddings, then the difference is much closer to 0, and so on. Yeah, so that is our finding by first just looking at the marginal distribution. But of course, you can do something that are a bit like fancier. For instance, to look at the KR divergence. We cannot look at the KR divergence between the two distributions because it's too big, but how about looking at the KR divergence between those per symbol conditional distributions? That is like this formula. So per symbol, like suppose you have already generated, until like point I-1, then you can look at what is the probability for generating the next token in the correct distribution versus in the output distribution of the GPT. You can calculate the KR divergence, and here is the result. And similarly, you can notice that if you use the vanilla GPT, then not only accuracy is bad, but also the KR divergence is bad comparing to others and so on. So this concludes the first result of the paper, that is, transformer actually learns such CFGs. So for the remainder of the talk, we'll be focusing on actually the how part. That is, how did transformer actually learn such CFGs? So before I go to the how part, actually, let me mention two kinds of critical feedbacks we have received since the paper showed up online. That is, some of the readers actually say that the result may not be that interesting because grammar is easy to learn, right? But I want to emphasize once again that we are not studying English or coding grammars, which are easy to learn because they can be locally parsed by greedy, especially coding grammar. Like, you can just completely parse it by greedy. You don't need any dynamic programming, right? But we are concerning some more ambiguous CFGs in this talk and in the paper. So we also received feedbacks from readers that say completely the opposite, that this result is impossible because the CFGs you created are very hard. Some of them say that, like, could you eliminate the possibility that maybe the model only memorizes some sentences instead of like learning the correct CFGs? But I want to really point out that there is no way for it to memorize because there are 10 to the 80 number of possible sentences in the CFGs, right? And remember, we also had the completion task. And if I give you like a prefix of 50 tokens and let the model to complete, it's going to be highly accurate on that. But for a model to even just memorize a solution for each prefix, this is already far, far beyond the number of neurons in the transformer. So therefore, like this cannot be a result of memorization. And another critical comment we received is that maybe the model just learns some easy part of the grammar, but not the hard part. So I want to defend once again by saying that like we really created synthetic data, right? In our synthetic CFG, there is no easy part. So if you look at English, for instance, there are a lot of English sentences that are short and even of the same grammar tree, like I bought an apple or I called a taxi. So those two actually follow the same grammar trees, right? But in our case, every two sentences will have negligible chance of following the same grammar tree because we have like 10 to the 80 of such parsing possibilities, right? And therefore, there is just no easy part. And we also don't have sentences that are short and so on. So that's actually one of the beautiful parts about studying synthetic data and so on. So yeah, that's my comment to some of the feedbacks of the paper. So let's now really go to the how part of our paper. That is, how do transformers learn CFGs? So to begin with, I need to introduce you some notations. That is, suppose we have this maybe input sentence like X, and suppose if you do dynamic programming, then you get the following like global parsing tree. Then I'm going to define something called NT ancestors or SLI to represent the tree node's name at level L for symbol XI. For instance, for the symbols here, then their NT ancestors on level 4 would all equal to 13. So that's the node name on this level for this sequence. And for instance, for the symbols here, then their NT ancestors on level 4 would equal to 15. But their NT ancestors maybe on level like 3 would equal to 18 and so on. So that's NT ancestors. And NT boundaries is another notion we introduced, or NT-end is actually a binary vector, so BLI equal to 1 if XI is at the NT-end boundary for level L of the CFG. So for instance, this position, this XI, is at the right boundary or end boundary for this subtree, that subtree, and that subtree, right? So therefore, like we have 1, 1, 1 here for level 6, level 5, and level 4. But it's 0 here because it's not at the right end boundary of this node 18. Okay, so that's the notion of NT boundary, or BLIs. So those two are very important notations that I will keep using them throughout the rest of the talk. So on the next slide, I'm going to show you that GPT, or language model, actually not only learns CFGs, but actually also implicitly learn those NT ancestor and NT boundary information. But before I even go there, let me motivate a little bit. That is, why do I care about those two notions? Think about it. Suppose you write a dynamic programming to do the parsing yourself, right? There are many ways you can do that, but here is at least one way. You can define dpIJA to be whether or not this sequence from I to J can be generated from a symbol A following the CFG rules. You can define it this way. And whenever you see, for instance, 1, 0, 0, 0, 1, and for instance, 15 sitting on the top, then that means that dpIJA equals to 1 for this segment from I to J. So this is actually a sufficient condition for the dpIJA equal to 1. So you can also write this like as a formula, right? But this is not a necessary condition. Notice that there may be some other sub-problems that satisfy dpIJA is equal to 1, but they're not on the global parsing tree of the CFG. So for instance, this segment, it could be maybe generated by some node 14, say like on level 4, but just it's not on the global parsing tree. Okay, so yet this sufficient condition actually gives you a backbone, or in some sense a minimal set of DPIJAs in which, like, as long as you know that they equal to 1, then that certifies that the input X is inside CFG, inside your language. Okay, in other words, suppose that I can convince you that the transformer actually learns also the NT-boundary and the NT-ancestry information. Then that means the language model not only learns the CFG, but actually also learns to certify a CFG. Just because by reading off from the BLs and the SLs, then you can read off what are those DPIJAs that equal to 1 that are also on this backbone, on this like minimal set, in which you can put them together, and that helps you to certify that the sentence X is in the CFG by just spelling out the entire like parsing tree. Okay, so this is the motivation for why like I care about those two notions. Now I want to show you how transformers learn such two things. So the way I'm going to convince you is by doing linear probing. That is, I take the pre-trained transformer, right, and then I feed an input sentence to the transformer and let it go over its decoder layers, in particular 12 layers for GPT-2. Then we look at the last layer, in which that gives us hidden embedding, hidden embedding of each token at the last layer, and we call it EI for the ith position. Let EI be a vector that is 768 dimensional for GPT-2 small. That's an encoding of this token on the 12th layer. And from there, from this last layer, we want to do probing by checking if there is a linear function over the EIs that happen to encode the BLs and the SLs for every CFG level L and for every position I. If so, then we know that the last layer, actually up to a linear transformation, has already learned and encoded such knowledge about the NT-boundary and NT-ancestor information. So that is the plan. Okay. If you think about it, I am using the entire encoding of the last layer to check if that encodes the BLI and SLI for each I. But one can ask for a stronger condition. That is, can I just use maybe the encoding of the, for instance, the 7th position to check if it encodes the BLs and the SLs for position I equals to 7. But I claim that this is information theoretically impossible because, for instance, if I only read until this point, so GPT is a decoder-only model, so it only looks at things to its left, right? So for instance, if I'm only at this position, I wouldn't be able to tell if my, I am able to tell maybe my parent is my parent and my grandparent, but maybe I'm not able to tell what is my grandparent and so on, right? So therefore, information theoretically speaking, you cannot just use the embedding at that particular layer to infer what is your NT ancestors for all the levels. And this is really why we need to look at the entire last layer to check if up to a linear transformation, that last layer encodes BLs and SLs for every level L. Okay, and how do we do this linear probing? We do it as follows. This is our probing technique. That is, suppose our goal right now is to fit BL and SL for a particular position I. Then we first freeze the pre-trained network, so we don't change it. We only do a probing, right? And here is how we do probing. That is, we apply a linear and trainable linear function to the output of every token position of the transformer. And this is the same linear function that is trainable of 768 dimensions. And then we apply a weighted sum to combine them to fit the BLs and the SLs. And here the weights are determined by a weight matrix that is also trainable, but the weight matrix does not depend on the input X. It does not depend on the sequence. It only depends on, for instance, if I care about the weight that goes from I to K, then it only depends on the position I and the position K. And there are many ways to parameterize this. For instance, for each position, say position I or position K, you can introduce a positional embedding like PI and PK, and you let them to be trainable. And then you can define like a softmax function, for instance, as a way for you to choose the weighting here. All right. So therefore the weights are trainable, but do not depend on the input, and the linear function here is also trainable, and it depends on the input x. So in the paper, we actually did something even a little fancier than this. That is, we not only support having like one linear function, and we also allowed the allowed probing to actually have multiple linear functions. I think we allowed for 8 linear functions to be there. And then we had also 8 sets of weights sitting in the front. And we use this as our actually probing function to check if that if this like 768 dimensional vector actually contains information about the BLs and the SLs for that position I. So the definition looks complex, but keep in mind that it's anyways but just a linear function over the EIs. And this can be viewed as a multi-head linear function that just will make the parameterization like easier to learn and so on. And also like it allows the input sentence to be arbitrary length. And then you only need like one set of linear functions to be trained and so on. So this is like our multi-head linear probing function. And we train this function to check if the embedding here can actually be used to fit the anti-ancestor and the anti-boundaries. And here is what we find out. We take more than like 100,000 samples to train those parameters, and then we tested on a disjoint set of samples. Here's what we find out. The first result here is that we confirmed actually transformers' hidden states do encode the anti-ancestor and anti-boundary informations. For instance, the anti-ancestor information that are the numbers sitting here, then all of those numbers actually are up to a linear function, up to this amount of accuracy, are linearly encoded in the last layer's embedding, just using that multi-head linear function that I created before. Okay, so this is like a first message, that is the anti-ancestor informations can up to, for instance, 93% to be learned, to be encoded in the last layer. And here, like the different columns represent the anti symbols at the different levels. For instance, NT6 means the S6, and NT5 means S5, and so on. And you see like NT2, which is the closest to the root, is the hardest to learn. So therefore, the accuracy is a little bit smaller, comparing to those anti-ancestor information on level 6, which are closer to the leaves. So they are much easier to learn. So this means that the model actually learns very well about the anti-ancestor information for those ones that are closer to the leaves, but not that perfect for the ones that are closer to the root, and so on. So this is our very first finding. And if you compare this to the baseline, which is you take a random transformer and then do the same like multi-head linear probing, then you won't get any good result comparing to this. Now, as a side comparison, we also did the same experiment, but for BERT. Instead of like GPT, which is a decoder model, the only model, we also looked at BERT-based model, in which case we used DBERDA, which is a better variant of BERT, using also a relative positional embedding. And that is trained on a masked language modeling task, which is to say that you mask out, for instance, like 15% of the tokens, and then the model doesn't necessarily look only to its left at the attention. It's a bidirectional model, so it looks at not only the symbols to the left, also the symbols to the right, and then try to recover what are the masked tokens. So then BERT-based model can also be pre-trained on our synthetically generated CFGs, right? But I claim that they fail, very crucially, they fail at learning those NTs that are closer to the root, comparing to the GPTs. If you think about it, this makes a lot of sense because when locally, like if you want to determine like what is the missing symbol, you don't need to parse the tree to a very high depth, right? You don't need to parse all the way to the root. You probably only need your surrounding like tokens for you to determine what is the missing token. So therefore, like a BERT-based model or a masked language modeling-based model, they're just by design incapable of learning something that are very deep in the context-free grammar. But if you do like a GPT, then the model will be capable of learning that. So this is like another important message from today's talk that I will also come back to this later. Furthermore, the next sub-result I want to show you is that, remember we have this multi-head linear function, right? So that takes as input basically the hidden embeddings of at every single position in order to probe the NT ancestor information at a single position. So this may look like huge because you're using a lot of information. So can we relax this a bit? In particular, let me ask, can we talk about a simpler task, that is to predict NT ancestors at NT boundaries, or in symbols, to predict SLIs at those BLs that equal to 1. So what do I mean here is that for those ones in the red, that means in particular, they satisfy a property that is if you read the input until, for instance, this point, then information theoretically you should be enough to actually determine those NT ancestor symbols in the red ones, because you have already finished reading the entire subtree rooted at 13. You cannot maybe determine like your grandparent is 18, right? Because you haven't finished reading that entire subtree, but you can at least like determine like maybe 13 and 12 and 8. And similarly, like if you were here, then you should be at least able to determine like your parent, maybe not your grandparent. So then for those NT ancestors in the red boxes, in principle, we do not need to look at the entire last layer in order to probe them, right? Then can we like just look at the encoding here to try to see if you can recover those hidden NT ancestor information? So this is what we mean, what we do by diagonal masking. That is, we can also force the weight matrix to be 0 as long as like I doesn't equal to j, or maybe we can do tri-diagonal masking. That is, whenever I minus j is more than 1, then we force it to be 0 and so on. So we can do this like diagonal masking or tri-diagonal masking, like addition on this top of this multi-head linear probing. And then here's what we find out. Namely, transformer indeed encodes NT ancestors at NT boundaries to a very good accuracy, like about like 99% accuracy. So this means, in particular, by just reading the 3 vectors sitting at those at the hidden embedding of the transformer at the last layer for those 3 positions. So this is tri-diagonal masking, right? It means just by looking at those 3 vectors, each of them of dimension 768. So that is enough for you to recover the NT ancestor informations that are the 13, 12, and 8. So this is pretty amazing. That is, the NT ancestor information not only is encoded in the last layer, but actually also encoded very locally around that point. So to conclude, I just showed you 2 results. Number 1 is that transformer encodes the NT ancestors in the last layer of the hidden embedding up to a linear transformation, okay, from the hidden states of the last layer. And at the same time, I showed you that transformer not only encodes that, but also encodes that at the correct position, that is at the NT end boundaries, by picking at most like 1 token. That seems to be enough for you to recover the anti-ancestors at the anti-boundaries. Just by picking like one more position, that's enough to uncover the anti-ancestor information. So that's the anti-ancestors. In fact, in the paper, we also showed that the same thing holds for anti-boundaries by also picking at most maybe one token position. So pictorially, this is what we found out. That is by looking at most like to the left by one token and to the right by one token, just by the three vectors, each of dimension 768, then that hidden space actually encode not only the anti-ancestors sitting here, but also the anti-boundaries sitting here for all the layers. And similarly, like if we were here, like it encodes everything here and everything there. So this is actually a very big finding, just says that the anti-ancestor and boundary informations are not only stored to a very good accuracy at the last layer of the transformer, but also very locally at the correct position, maybe up to at most one position. So another thing I'm not showing you, but it's in the paper, is that such information, we also showed that the anti-ancestor and boundary informations were actually encoded in a progressive manner with respect to the training epochs and the transformer layers. That is, the more you train it, then the more accurate it becomes, and the layers closer to the leaves are learned first, and the layers are closer to the root are learned like last, and so on. So it's learned in a progressive manner. So to conclude, I just so far showed you the following. That is, as a byproduct of the pre-training process, transformer not only learns to parse the CFGs, but actually also learns to certify that a sentence is in the CFG by just learning the anti-boundary and anti-ancestor information as a byproduct. Okay, and this is even true for CFGs that are very long, like say having hundreds of tokens. And in the remainder of the talk, let me show you how did this happen. So far I just showed you, transformers learn CFGs, and how did that happen? Because transformers learned the anti-ancestor and anti-boundary informations. But let me further ask, how did transformers learn the anti-ancestors and the anti-boundaries? To answer this question, we have to look at the attention pattern, okay, to explain this how part. So this is our result 3, in which we first showed you a very simple thing. That is, if you look at the attention weights, then transformers' attention weights are primarily influenced by the token's relative distance. So this may not sound that surprising. So for instance, if you look at the different layers, and each layer has 12 heads, so the 12 rows sitting here represents the 12 heads for layer 7, then if you look at the attention weights, you see that there is a multi-grid like pattern. That is, some heads prefer tokens that are closer, and some heads prefer like tokens that are further away, and so on. You may not find this like surprising, but let me emphasize that this holds even if you just pre-train your model on the CFG data, and even if like you pre-train your model just using an absolute position embedding. That is the vanilla GPT-2. So if you use like relative positioning embedding or rotary embedding, then this is of course true. But even if you just use absolute position embedding, and even if you just use the CFG data, which only has syntactics but no semantics, then also this pattern is true. Okay. So it is actually because of this observation, we actually tested what is the performance of GPT with just a positional-based attention, or maybe a uniform-based attention that is of a multi-grid kind of style. And we noticed that that can indeed learn the CFGs to a great accuracy and so on. So this is like a side result from the paper, in which we emphasized on the importance of having such positional-based attention just for the purpose of learning CFG alone, not to say like for even harder tasks and so on. So because of this property, that is, attention patterns have such position bias, and therefore let's now remove the position bias from the attention, and then to study what is really left behind. Here's how we do it. So let A denote the attention weights, that is ALHJ to I, to denote the attention weights for position J to I at layer L and head H of the transformer on input X. Okay, let A just be the attention weight, and then we can calculate the average of A based on the relative distance. Let P just, its average over all of the J and I's whose distance equal to P, and then we can subtract it and define the remaining part to be B. So let B just be the A, but minus the average of A, but with respect to the same relative distance. And let us study how does B look like. So this is after removing the position bias from the attention matrix. We have 3 findings. The first finding is that we notice that the B value exhibits a strong bias towards tokens at the anti-end boundaries. So this is what we mean. That is, we look at, for instance, 2 data sets for this talk, but in the paper you can find more. We can look at different transformer layers and different heads, okay? And each cell here is a 5 by 5 cell. It represents the average value of the B values over those J goes to I attentions, such that I plus some value delta is at the anti-boundary, or also known as anti-end, at CFG level L. And here the 5 columns represent delta equal to -2 until +2, and the 5 rows represent L equals to different CFG levels. So here the important message here is that you notice that the model has a very strong bias, strong preference over delta equals to 0. So therefore it really favors, whenever it sees like attention from J to I, it really favors those I's that are exactly at the anti-boundary. We tried -2 until +2, but the largest value is obtained when delta exactly equal to 0 at the any different level of the CFG. So that's our first finding. That is, the the B values exhibits a strong bias towards those token I's that are at anti-boundaries. Our second finding is that the B values, furthermore, actually favors those pairs J and I's in which both of them are at anti-ends for some level. So here is the result. So again, we look at different levels, different layers of the transformer and different attention heads. And here, each cell here is 3 by 3. So it represents the average value of the B's over those J attend to I, such that I plus some delta 1 and J plus some delta 2 are both at the anti-ends for level L. And here the rows represent delta equal to delta 1 equal to -1 until +1, and 3 columns represent delta 2 equal to -1 through +1. So once again, you see that the model has a strong preference over delta 1 and delta 2 exactly equal to 0. Okay, so therefore it favors pairs of I and J's in which J attend to I, for instance, in which both of them are at anti-ends for not only level CFG level 2, level 3, and for different levels. And we also see that different transformer layers and different transformer heads may have a different preference. Like some of them may learn to attend NT2 to NT2, and some of them may learn to attend like NT5 to NT5, and so on. So that's our second finding. The third finding, in my mind, is the most striking here. That is, the B value actually favors adjacent NT-end pairs. So not only like it favors like IJs that are both at NT-ends, but it actually favors those ones that are also adjacent. So I need to define what do I mean by adjacency. This requires a little bit definition. That is, suppose there is like a parsing tree of the CFG parsing tree of the sentence. Then let's say that xi is at the deepest NT-end for some level L, if L is the smallest value such that xi is the NT-end for that level. So therefore, like this symbol, for instance, is the deepest NT-end for this level, and this position is the deepest NT-end for this level, and so on. Okay, so that's a notation. And now we can define the end-to-end b-value to be the average of the b-values over samples x and those pairs j attend to I, such that they are respectively at the deepest NT-ends on the CFG levels, L prime go to L, in which also they are at a distance r based on the NT-ancestor indices at level L, at the destination level. So let me pictorially show you what this means. If I consider like this position attend to that position, then they are both at NT-ends of level 6 as the deepest, and they are, I define them to be of distance 5 because I need to jump like 1, 2, 3, 4, 5 to go there. But if I talk about two NT-ends at different levels, for instance, from here to here, then I use the destination level as the count for the distance. That is, I also need to jump like 1, 2, 3, 4, 5, and therefore I say from here to here, it's NT3 to NT6, also of distance 5. Okay, but if I go from here to there, then it's NT6 to NT4, but it's of distance 0 because I use the destination level as the count for the distance, and the distance is 0 because I do not need to jump over anybody on level 4. But if I go from here to there, I say the distance is 1 because I need to jump over like 1 NT-end at level 4. So that's my definition of the distance. So here is what we found out. That is, we plot this end-to-end b value, and we average it over all the layers and all the heads. In the paper, you can see the more detailed result without averaging over the layers and heads. But here is what we found out. So the columns represent from which layer to which layer. So from, remember, we consider like the NT-ends from level like L prime to level L, right? So this is what the columns represent. The rows represent the distance that I just defined. And we can pictorially look at how large the b values are averaged over the layers and the heads. So first notice that there are some empty cells. So those are the cells that do not have any value. Because, for instance, here, if you look at from NT3 to NT3, then the minimal distance is 1. So you don't have distance 0 because you're not crossing two layers. You're not crossing two levels, and therefore, like, you don't have any value here. And for instance, here, if you look at like NT3 to NT3, then the maximum distance is 7, and therefore, if you go to distance 8 and so on, you don't have any values. So for such reason, there are some empty cells. But the most important message here is on these two rows. That is, you can look at here by and conclude that the b values really favor those NT-ends to NT-ends. So maybe the NT-ends are at different levels, but no matter how different they are, then the b values really favor them that are at the minimal possible distance. So if the minimal possible distance is 0, then it favors that at 0. But if the minimal distance is 1, then it favors that at 1, and so on. Okay? So this is striking because, remember, I have already removed the position bias from the attention. So if I do not remove the position bias, then this is obvious, right? Because attention will favor things that are closer. But even after removing the position bias, I still see this. That is, the b value favors adjacent NT-end pairs, even across layers. So that is like concludes like our result number 3. That is, attention favors adjacent NT-end pairs. So now, like, I'm going to use my result number 2 and number 3 to show you as a corollary that this gives actually very strong evidence that transformer actually learns to do dynamic programming. Okay, so how can I say this? Recall that what is dynamic programming? It has two parts, a storage part and a recurrent formula part. A storage part, in today's talk, I can use the following. That is the DPIJAs. It can be, whether or not it can be a 0, 1 value representing whether or not the xi until xj can be generated from a symbol A following the CFG rules. And remember, like I showed you this sufficient condition for the dpij's to be 1. That says that I told you a few slides back, that is learning, if I can show you that the transformer can learn such anti-ancestor and boundary information, that means that the transformer actually learns a backbone of the necessary dpij's on the correct CFG parsing. So for instance, this one and this one and that one, those ones are on the correct CFG parsing, and they are actually learned by the transformer. So this I already showed you in result number 2. And also keep in mind that we intentionally did not probe over those dpij's that are not in the backbone. So for instance, this segment could be also satisfying dpij's equal to 1, but it really depends on how you implement the DP. Even when humans like write DP, for instance, we have some inner loops for search and so on, then we can do pruning, right? As long as we find out, for instance, the dpij for this segment can be solved by these 2 segments, then we can stop. We do not need to further like calculate any other subsegments and so on. So therefore, depending on really the pruning and depending on, for instance, the order of the for loops and so on, then for those ones that are not on the correct CFG parsing trees, they may not even need to be calculated. And this is why we do not probe them, because we cannot say for sure, for instance, which version of the DP that the transformer is implementing, because there are infinitely many of ways to implement it, depending on the order of the pruning and so on, right? But we anyways verified that for those ones that are in the backbone, then those necessary dpij's are learned by the transformer. So one way to see this is that the transformer actually learns a backbone of the necessary dpij's shared by all versions of DP implementations. Once again, like we're not saying the transformer is implementing a particular version of DP. We're saying that regardless of which version of DP is implementing, it has to learn those dpij's that are in the backbone. And indeed, we probed and showed that they are learned. So that is like on the storage part. Now, on the recurrent formula part, is there any way to also define like a backbone shared by all variants, all implementations of the DP? So that seems hard, but let me give you at least examples, right? And here is one way to write down the recurrent formula. That is, we can say the dpij equal to 1 if there exists 2 separating points like I1 and I2, such that there is a CFG rule that says A can go to, say, B1, B2, B3, and it happens that the 3 segments are all equal to 1. So for instance, if you have these 3 segments that satisfy dpij ij b1, ij like b2, b3 equal to 1, then you can conclude that the parent, the dpij equal to 1. So this is one way to write down the recurrent formula. But if you directly implement this recurrent formula, that has a time complexity of n to the 4th power, because you need 2 inner for loops, right? The I1 and IJs. And for those of you who have played with this DP like before, you may recognize that there is a way to lower this down to n cubed, and this is the so-called binarization technique, in which you have to do some merging. That is, you merge the rule by like creating some auxiliary node by merging maybe B2 and B3, or merging B1 and B2. So if you do it that way, that can reduce the time complexity of this recurrent formula to be n cubed. But which way do you merge, right? This is, once again, like it depends on how you implement the DP. And I'm claiming that no matter which way you implement, if you do it like this way, then you have to, at some point, like from this position, you have to do a memory link to read some knowledge that has been stored at the previous NT-end position. Or if you do this merging, then at some point, for instance, if we're here, you have to also read some information. You have to do a memory link to that position. So therefore, this is precisely why that we have checked, for instance, transformer actually in the attention pattern really prefers adjacent NT-ends, because regardless of how you implement, for instance, the binarization and any other any other subtleties about the recurrent formula, you really have to do memory links between adjacent NT-ends regardless of the DP implementations. So this is like how like we try to convince you that also it doesn't matter which DP implementation you do, it doesn't matter like which recurrent formula you write. Actually, there is a shared pattern that is a transformer or a DP algorithm has to do such kind of memory links between adjacent and NT-ends, and we checked indeed transformer actually has such a pattern. So that is on the recurrent formula side. But finally, I want to point out that just DP alone is only capable of parsing a CFG, but learning a CFG is actually a harder task, in which like you also need to learn how to generate the next token. So for instance, if you are here, then what is the next token, right? Over there, you probably only know that your parent is 9 and your grandparent is 10. But you probably also want to look at what is your uncle, because you don't necessarily have information about your grandparent. So you might want to look at your uncle before you can generate what is the next token. So that is necessary because you know, there may be two different rules. For instance, it could be 15 that generate 10 here, or it could be 14 that generate 10 here. So I need to distinguish between the two in order to know what is the next node I want to generate on this level. So for such reason, a generation task of CFG also needs to look at you know, things that are, for instance, on the uncle level of the CFG tree. So that means that we also need to have memory links between adjacent NT-ends at different levels in order to implement the generation process of CFGs. And indeed, we just checked on the previous slide, or in result 3, that the attention not only favors the NT-ends at the same level, but also the NT-ends at different levels. And this is how we also verified that the generation process of the CFGs also follow this pattern of dynamic programming and so on. So that concludes the main body of the talk. Okay, so let me now show you some extensions. The first extension I want to show you is very simple, is what we call and what is known as implicit CFGs. That is, suppose that not only like we have a CFG that generates terminal symbols, but say each terminal symbol is also associated with a bag of words known as like observable tokens. So for instance, one could be associated with the set of verbs, 2 can be associated with the set of nouns, 3 can be associated with the set of adjectives, and so on. And in particular, the observable tokens can also overlap. Okay. And now we can study like if we pre-train a GPT on such observed tokens instead of like looking at the terminal symbols, but you look at the observable tokens, or for instance the actual words, right? Then can the GPT actually learn the CFG? The answer is that yes, the GPTs can also learn such implicit CFGs, and the way it does that is very simple. It just encodes those observable token information on the token embedding level. You don't even need to go deeper in the transformer. Namely, like we actually plotted, for instance, we have 3 terminal symbols, right? And we have 8 possibilities for a word, like if it belongs to the bag of the words for the first one, the second one, and so on. Then for those words, we checked about their relative correlation on the token embedding level, and we noticed that you know, for the words that are of the same type, for instance, those ones that are only verbs but not noun and not adjectives, then they actually correlate a lot with each other and so on. So therefore, we conclude from here that even if you have implicit CFGs in which like you do not observe the terminal symbols, you only observe the observable tokens, and they can even overlap, but then still such information would just be stored like on the token embedding level, and then after that, then it just becomes the same as before as the original CFG. So that's like our first very simple result on implicit CFGs. The second result, second extension here is on what we call robust CFGs or corrupted CFGs. So here is the task. That is, suppose we're given like a prefix from the CFG, but we corrupt it by randomly flipping, say, 50% of the tokens, and then let's see if a pre-trained GPT can be used to still complete the sentence. For instance, we can feed the CFG with a prefix here, but we can corrupt maybe 6 of the tokens by randomly generating it from the set of 1, 2, 3, right? And we can check if the GPT is capable of completing the entire sentence, so that if you append it by the original correct prefix, then is it still in the correct CFG language? We can do this task, right? And we can study pre-trained GPTs of 2 different kinds. We can study the ones that are pre-trained using just clean data, using the correct CFG. We can also study the GPT that are pre-trained using robust data. So, for instance, you can you can let like some gamma fraction of the pre-trained data to be perturbed, and then pre-train the model on this perturbed data. And there are many ways to perturb it. You can use the same perturbation as here, that is to perturb it on the terminal symbol levels, that is to randomly flip each terminal symbol, or you can perturb it on the NT level, so to look at some inner level of the CFG and randomly flip it. In this way, like even the length of the sentence will change, or you can do some even deterministic perturbation instead of a random perturbation, say on the NT level and so on. So we tried at least 3 different perturbations in the data. And here is the result. On the rightmost, there is the clean trained model. And on the left, there are 3 kinds of robust trained models with respect to 3 different kinds of perturbations. So let me read this with you. The first very important finding here is that if you take a clean pre-trained GPT, then it's not actually very robust against corrupted prefix. That is, you only have a 30% accuracy. If you feed the model with a prefix of length 50, and you let it to continue generation, then only with 30% chance it's going to complete the sentence correctly, okay, with corrupted prefix. And instead, if you use a robust pre-trained GPT, whichever version you choose, say a robust GPT, and actually, regardless of the gamma, the percentage of the perturbation of the data you put in the training, then in all the cases, if you use a low temperature in generation, like 0.1 or 0.2, then the accuracy is, the completion accuracy is much better than 30%. Okay? And you also find out this very interesting rule, that is, if you use temperature 1, then the accuracy suddenly goes to 0. So let me explain what's happening here. So in fact, we noticed that GPT is capable of learning actually a mode switch at temperature 1. That is, if you feed the model with a correct prefix, so this is without corruption, you give it a correct prefix of length 50, then it's capable of completing the sentence with very good accuracy. Unless, like, if the model never sees any correct sentence, 1.0 means like your robust training has only seen like corrupted or only seen like perturbed data. But here in all the other cases, you have very good accuracy if you have a correct prefix. And in contrast, if the model is given a corrupted prefix, it almost always spells out also a corrupted completion. Okay, so it actually learns a mode switch. If you give it a correct prefix, it says something correct. If you give it a corrupted prefix, it says something also corrupted. And of course, if you don't give any prefix, then the model actually has a probability of choosing to say something corrupted or say something correct, and the percentage of the the percentage of how much it does so actually it's proportional to how much it has seen corrupted the data in the training set. So this is actually a very interesting finding because it connects very well to practice. Namely, for instance, if you take Llama, that was Llama 1, I think, when we tried, then we noticed that if you feed Llama with a corrupted sentence, like the one with a lot of grammar mistakes, then it actually goes to that grammarly mistake mode. That is, it will also complete the sentence with grammarly incorrect completion. And for instance, you see even was here that never actually showed up before. So therefore, like it not only learns to say grammarly incorrect completion, it actually also learns to say like with new grammar mistakes and so on. So this is what we found out here that very interestingly connects to practice. That is, if you use temperature 1, then the model actually learns to do this mode switch. That is, it's going to detect if you're in a grammarly correct mode or grammarly incorrect mode, and it's going to follow like also using that mode if you use temperature 1. And that's why in practice, for instance, we probably really want a temperature that is much lower than 1 for our real life applications and so on. And also in practice, we really had better add those grammarly mistaken data into the training because that will improve the model's robustness against, for instance, grammarly incorrect data and so on. So actually, I think the findings here are also very important and do connect to practice. So the third result, the third extension I want to say is to compile to English CFGs. So as I said, actually, at the very beginning of the talk, the English CFG is very easy. And in particular, its length, this is like an average length of the CFG, of the English CFG, and this is the 80% percentile of the length of the English CFG. But our CFGs are much longer. Let's say the CFG3 data is much longer. And here, like to make this comparison maybe a bit more precise, let me explicitly say like what CFG we used from the English CFG. That is, we derived it from the Pantry Bank dataset, in which we removed all of the CFG rules that are showed up fewer than 50 times in the data. That results in this number of symbols and this number of CFG rules. And we also binarize it so that after the binarization, it has this number of symbols and rules. So we removed those like less frequent CFG rules just for the same reason as our CFG3F, because in this paper, we do not want to focus on those ones that have very low probability to show up. We want to disentangle the issue of the probability for a rule to show up versus the difficulty of the CFG, like from the tree structure and so on. In any case, so we construct the CFGs in this way. And if you study the accuracy of learning such English CFGs using GPT-2, here's what you'll find out. So on the rightmost, you have GPT-2, which has 12 layers and 12 heads, and each head is 64 dimensions. So that is about 100 million in size for the GPT. But in fact, you can notice that if you just use a 100 kilobyte size the GPT of like 2 layers and 4 heads and so on, then you can already learn the English CFG to a very good accuracy. So the first row is generation accuracy. The second row is completion accuracy. And in contrast, if you look at CFG3F, then you really need a very large GPT-2 to learn such CFG. So I hope this is a convincing experiment to show you that our CFGs, the synthetically constructed CFGs, are much, much harder than the English CFG that people usually talk about, and so on. So that is our comparison to the English CFGs. The next extension, the final extension I want to show you is what about other CFGs? So in the paper, we not only actually looked at the CFG3 data family that I have been using in this talk, but we also looked at some CFGs that are not that balanced and also maybe a bit deeper, but with rules of length 1 or 2, and so on. So we created actually more than 20 CFG, synthetically constructed CFGs, and did some similar experiments. For instance, the accuracies, you will see also similar patterns, and the GPT, the relative and the rotary embedding versions also perform much better comparing to the vanilla version. And we also did some probing to those other versions of the CFGs, and so on. So therefore, like our conclusions not only just hold for one CFG, but at least for many of the CFGs we constructed in a few different ways, and so on. So to conclude, today I showed you how to use synthetically constructed CFG data to actually perform controlled experiments to reveal how language models can learn some very hierarchically defined language. So this is very different from, for instance, the induction head hypothesis, which is really talking about interpretability of a transformer on the token level. But we're looking at something that are much, much harder, like hierarchically defined language. And we also introduced some probing to show you that the inner states of the transformer really do correlate with the abstract hidden structure of the sentence, i.e. the NT singles in this talk. And very surprisingly, we found out that the way transformer actually learns to do this, learns this language is by doing something very, very similar to dynamic programming. We provided, I think, very convincing evidence for that. And also, like, I want to emphasize that the CFGs we studied in this paper are not simply language or coding grammars, which are very easy. So we studied a very synthetic and very challenging, long and ambiguous families of CFGs. Okay, so this is actually calls back to this difference between physics and ethology that I talked about at the very beginning of the talk. That is, by doing physics, we really allow ourselves to design data of our own way to test the ability of language model to the greatest extreme. But in contrast, if you play with ChatGPT or even GPT-4, I suspect that it's much, much harder to make a conclusion like this, because like English grammar is too easy, right? Then it's much harder to make such inner probings and to make conclusions as scientific as this paper. And finally, the probing technique we introduced in the paper may be of independent interest, right? So it allows you to actually probe from the last layer, but of varied length and so on. And very surprisingly, many of the results we found out from here actually connect very well to practice. So number one, we emphasize on the importance of doing rotary embedding or relative attention instead of the original absolute positional embedding of GPT-2, for instance. So I know that this is already like widely known in practice, but we pointed out that even just by looking at the syntactics level, by looking at the grammar, it's still like very important to do this. Okay, so therefore we should really abandon like absolute positional embedding. That's number one. And number two, we also pointed out this major difference between language modeling versus masked language modeling, such as BERT, in which BERT is just incapable of learning something that are very deep in the logic. But the GPT is capable of doing that by using this example of CFG. And finally, in one of the extensions, I told you that our results relate a lot in practice to robust and corrupted languages. That says two things. Number one, whenever you do pre-training, you had better also include corrupted data, like say English sentences also with grammar mistakes. And during testing, you had better really use a low temperature. Otherwise, the model is going to learn a switch between grammatically correct and incorrect data, and so on. So thank you so much for your attention. Bye-bye.